Okay, thank you very much for the introduction, and thank you for the organizer to inviting me for this workshop. So I'll discuss the proving mixing time for the Glauber dynamics via a recent new technique called spectral independence. And this talk will be also related to the following two talks, which gave a lot of reproof and also improvement for the results here in this talk. And so most of the part will be based on joint work with Quiquilio and Eric Rigoda. Okay, so this is the outline for my talk. So I'll be mainly discuss the hardcore model over independent sets of a graph as an example. So I talk about a little bit about phase transitions and also the phase transition for the mixing time of the Glauber dynamics, and how do we use spectral independence to establish rapid mixing for this Glauber. So here's the hardcore model. So the hardcore model will gives like a distribution over all the independent sets. So we will use G to be a graph, and we assume we have a bounded degree graph with maximum degree delta. We consider the set omega of all the independent sets of the graph G. So just recall that independent sets is a subset of vertices where every pair of two vertex will be non-adjacent. And throughout the talk, I'll use a red dot to represent vertices that are contained in the independent set, and that's called occupy vertices, and the blue hollow dot to represent the unoccupied vertices, which are those not included in the independent set. And I also use lambda as a weight of vertex called fugacity. So we will be interested in basically the Gibbs distribution over all independent sets, where every independent set will receive a weight in the form of lambda to its size. And here Z of lambda is the normalizing constant of our distribution called the partition function, which is obtained by summing over all the independent set, and every independent set contributes lambda to its size. So this is also called the independence polynomial. Okay, so here is an example where you have a graph which is a cycle of length 4, and independent sets include like size 1 independent set, which is a single vertex, or size 2 independent sets, which are the diagonal pairs. And the partition function just kind of seeing that there's one size 0 independent set, which is the empty set, and 4 size 1 independent set, and 2 size 2 independent set, which are the two pairs of diagonals. Okay, so this is our model. We study like mainly the sampling problem, but which is also related to the counting problem. So the counting problem is to try to compute, given an input graph and the lambda, try to output the partition function, or say the independence polynomial. And the sampling problem is to generate the independent set from the Gibbs measure, from the Gibbs distribution. So this type of problem is typically huge, typically hard, because the size of the set omega, all independent sets, has exponential number. So exact problem is hard, and we usually study the approximate version, where we try to approximate output like an estimate of the number of independent sets, or try to generate a sample approximately from the target distribution in total variation distance. And the two approximate version problem are basically polynomially equivalent to each other. And also some intuition is that when your parameter lambda is pretty small, this kind of problem will be easy, because most of the time you will see small independent set. Okay, so lambda is small, is favoring small independent sets. So for small lambda, the pair problem should be easy, and for large lambda, you should be hard, because you will see large independent set. And in particular, consider like lambda tends to infinity, then the Gibbs distribution here will be basically like a distribution over all the maximum independent set, which will definitely be hard because finding a maximum independent set will be hard problem. So this is a problem we study. We will be focusing on how to generate samples from the Gibbs distribution. And it turns out that this computational problem is related to certain phase transition happening on the infinite regular tree. Okay, so I just gave a slide, discuss briefly about the phase transition for the hardcore model on the infinite data regular tree. So what happens is that you can also define a Gibbs measure for the hardcore on the infinite graph, which is the infinite tree here. And also there's a certain phase transition threshold, which is roughly E over delta. Delta is the degree of the tree. And you can obtain this threshold by considering like a finite tree of height h and consider what's the probability of the root when you have an even height tree or odd height tree. So the even and odd is simply because like this anti-ferromatism property of the hardcore model, basically like if your children is all unoccupied, then you are more likely to be occupied, and your children is occupied, then the parent is unoccupied. Okay, this is basically because of this property. So you consider the even height and odd height tree. And what happens is that when lambda is small, you will have a decay of correlation from the leaves to the root for a finite tree. And also for the infinite tree, this is the region that you have a unique Gibbs measure. For large lambda, you will have stronger correlations for finite tree, and also you have multiple Gibbs measure. Okay, so this is some background about phase transitions for hardcore model on the infinite regular tree. So what happens is that if we look at the computational problem for bounded degree graph G, the approximate sampling and counting problem. So the same tree uniqueness, non-uniqueness threshold also marks whether or not you have a polynomial time algorithm or it's computationally hard. So for all graphs of maximum degree delta, when lambda is smaller than the critical value, we know that there exists a polynomial time approximate sampler and counter. And for lambda is greater than the threshold, it also shows that it's actually NP hard for approximate sampling. Okay, so this is like a phase transition for the counting and sampling problem for hardcore model on bounded degree graph. Okay, so there's more details about algorithmic approaches. So for lambda smaller than the critical value, there are actually many more type of algorithm, but here I'm only mentioning three of them. So there's a correlation decay approach. This is approach by Weiss. It's also like the first algorithm which work up to the uniqueness threshold. And so this type of algorithm using like similarity between the graph and its corresponding trees of self-avoiding walks, and exploring the correlation decay property to give an algorithm. The second, polynomial interpolation. This is due to Barvanov. So this type of algorithm using zero freeness of the partition function and find the Taylor approximation of the log of the partition function. And in this talk, we discuss like a very simple randomized algorithm, which is basically running a Markov chain to generate an independent set. And so compared to the previous two algorithms, so the previous two algorithms, both of them are deterministic. So they do not use any randomness, but the pain is that they have like pretty large concurrent time because the exponent in n also depends on the maximum degree delta and also the little delta, which is like the slackness of the parameter. But for Glauber, it will be very fast, so it will converge in n log n steps. Okay, so let me introduce this Glauber dynamics, also called Gibbs sampling. So what we did is basically running a Markov chain to generate an independent set from the distribution mu. So what it does is that very simple. In every step, it will pick a vertex uniformly at random and try to update its status, whether occupied or not, given the condition of all the other vertices. Okay, so for example, I choose this vertex and I just forget its current color, or by color, I mean whether it's occupied or not occupied. And then I'll try to update it using the conditional Gibbs distribution at this vertex. Okay, so all the other vertices will still be fixed. And I use this conditional distribution and then have an update. Also, sometimes you will try to update vertex, which already has a label that has been occupied. So since we are moving this chain in the space of all independent sets, this new vertex cannot be occupied. So it will be always unoccupied to make sure that you are always having an independent set. Okay, so this is dynamics. And it will be relatively easy to show that the chain is ergodic and it will converge to the Gibbs measure mu using the correct update rule or update transition probabilities. And we will study the mixing time, which you can think of like the number of steps it takes for your distribution, for your current distribution at time t to be very close to the target distribution, the Gibbs measure in total variation distance, even when you're starting from a worse configuration or a worse initial distribution. Okay, so this is the Glauber dynamics. So our main result can be stated as like when lambda is smaller than the critical tree uniqueness threshold with the selectness factor parameter delta, then the mixing time will be n log n steps. So this also like certain, in some sense, complete this figure where lambda is more than a critical value. You have a very simple randomized algorithm in n log n steps. And also for large lambda, we know that the Glauber can require exponential steps in some graphs. And also it's a regime that is NP hard for approximate sampling and counting. Okay, so this will be like the main theorem or result I'll be discussed in today's talk. So to actually like prove such a result, we will actually have like a much more general statement using the spectral independence approach. So we will actually consider like a Gibbs distribution of some pairwise spin system, which I also call like undirected graphical model. So these are like distributions obtained from like a graph, and every vertex will receive labels or say colors such that the weight of every coloring is obtained by the nearest neighbor interactions. So if you are not familiar with them, you can just think of like the hardcore model, or you can think of like colorings of graph, proper colorings of graph, uniform distribution of proper colorings. And so this talk I'll be mainly discussing maximum degree to be bounded, which is some constant data. So we'll assume that two conditions. The first is that the distribution mu has some marginal bounds. Roughly speaking, this says that every vertex, the marginal probability, or say the conditional marginal probability, where all the other vertices are fixed. So this type of marginal will be bounded away from zero. So this is usually an easy to satisfy condition. And second, and more important condition is the spectral independence. So this is a notion proposed by Anarilio Oviatsgaran. And so this says, this is also trying to describe this property of correlation decay, which will say that for you look at the two vertex and you look at their correlation or say covariance, meaning that the event whether they are both occupied or non-occupied, and this correlation should decay with respect to the graph distance. But spectral independence we'll try to describe such a decay of correlation property in a spectral way. So I will define these two notions in more detail very soon. So our main, like the general version of our result will be saying that for any such distribution where you have marginal bounds and spectral independence, the Glauber will have mixing time analog gain. Okay, so in the next two slides, I'll discuss a little bit in more detail the marginal bound and the spectral independence we use. Okay, so the marginal bounds basically just wants that all the marginal probability to be at least something. Okay, so so here you look at all the vertex and you look at probability this vertex is occupied or not occupied, and we want all such probability to be lower bounded away from zero. Okay, and all actually we need something more, which is called the pinning. So we also actually need that this property to hold not only for the original Gibbs distribution over all independent sets, we also want it to hold to under any conditioning on such few numbers of vertices. So this is called pinning, which is just a conditioning measure. So the pinning will be for hardcore model will just be fixing some vertices to be occupied and some other vertices to be unoccupied. And for hardcore model, there will be a very much easier way to understand it because you fix a vertex to be unoccupied. And look at the conditional measure. This is equivalent to just remove this vertex V. And if you fix a vertex to be occupied, this will be equivalent to like remove this vertex and all its neighbors. Okay, so for pinning, we will just be considering all the induced subgraph, and we want that in all the induced subgraph, the Gibbs measure will have this marginal bound we want. Okay, so this is the pinning and the marginal bound. And the next is the spectral independence, which will be saying that, so we will need to define this influence, or say pairwise influence between two vertex. So we take U and V, we look at the influence from U to V, what just means that how much the marginal probability of V will be changing given two different events that U is occupied and U is not occupied. So which will be like the difference of the marginal probability of V being occupied, conditioned on U is in sigma and U is not in sigma. So this is like a natural description of the influence from U to V. Okay, so once you have defined this influence, you will have like an n by n matrix, and the spectral independence will be just saying that the maximum eigenvalue of such a matrix is upper bounded. And so this notion is given by the previous work of Anarilio Oviesco-Ren. And there's a very novel approach to like a framework, a very novel framework to show like polynomial and rapid mixing of the Glauber dynamics. So I'll give two remarks. So the first is that the influence matrix we have is not symmetric. So basically the influence from U to V is not the same as V from V to U. But this kind of matrix is also like closely related to the covariance matrix, or say the correlation matrix when you have like two spin system. The second is that this matrix will always have a real eigenvalues. So one way of seeing it is that you can actually show the eigenvalue of this matrix is the same as the correlation matrix. So all the eigenvalues will be real. And another way to see it will be like what I discussed a little bit later is that this matrix will also correspond to a certain random walk, which can be obtained by taking the transition matrix of this local random walk and minus subtract the top eigenspace. So all the eigenvalues will be real, and the spectral independence will be just upper bounding the maximum eigenvalue. Okay, so this will be our main result, saying that when you have spectral independence. We have also like with bounded degree graph and the marginal bounds, mixing time will be n log n. So usually if you have bounded degree, then usually you always have this marginal bound because the degree is bounded. And usually the harder thing is to show spectral independence. So I also want to mention that in a lot of recent work, actually the two talks after me, there have been a lot of improvement on this kind of theorem. Basically, we can try to remove the dependency of the maximum degree delta or the marginal bound in some of the special cases, in particular, including like the hardcore model and the easing model, and like the general two-spin system. So for these type of like binary state space, there's a way to remove the dependency on the maximum degree delta and also the marginal bound. But here in this talk, I'll be still doing the bounded degree case and also with the marginal bounds. So the remaining talk, I'll be discussing like a very high level idea. How do we prove this such a mixing result? So is there any question at this point? Okay, so let's move on. So the approach I'll be mentioning will be actually mostly from the ideas in the original paper of Anarelio Viesgoren. So their way of studying the Glauber dynamics is to fit it in the framework of high-dimensional simplicial complex. So here I just discussed this framework in the special case of like a Glauber dynamics. So instead of the hardcore model, I'll be considered like a very general two colorings of a graph. Okay, so you just consider we have a graph which is a triangle, and we try to label all the vertex by two colors, or say two colorings of the graph, not the proper one. And there will be some distribution over the two colorings. And the Glauber dynamics can be understood in this way, which is that you have a configuration at some time, and you move to another one of the other three configuration, which are obtained by just selecting a vertex uniformly at random and remove this vertex. Okay, so you will reach one of the three configuration. Say more precisely, it's a partial configuration with one fewer vertices, and you will go to this, and then you will try to go back by recoloring this vertex. And when you try to go back, you will update, you will go to the correct state with the using the conditional marginal distribution. Okay, and so to summarize, you can understand one step of the Glauber dynamics as actually moving between X3, the set of full configurations where all the vertices are colored, and between X2, which are the partial configurations on two vertices. So where you will select a two vertex graph and color the two vertices. And this is basically called the downwork if you are in the language of like simplicial complexes or high dimensional expanders. So the Glauber dynamics can be just understood as this random walk between X3 and X2 and then back to X3. So the down step will be going from 3 vertices configuration to a 2 vertices configuration. And the up work will means from 2 to 3. Okay, so this is like understanding of the Glauber dynamics. But in fact, you can do a little bit more. So you can actually consider this type of walk in not just between 3 vertex, but actually for any k, you can consider this random walk between k vertex configuration and k minus 1 vertex configurations, which is actually a very natural thing when you study like high dimensional expanders. Okay, so for the example here, I just mean like you can also consider the random walk between partial configurations on 2 vertices and partial configuration on 1 vertex. Okay, and you can do this type of random walk. And when doing the up work, going from 1 vertex to vertex, 2 vertex. So this time, not only you need to figure out like the color, you also need to first figure out which vertex you will try to update. So we will first like select one of the vertex and then select its color. So you can also define such a down up work, but between 2 vertices and 1 vertex. And also finally, like between 1 vertex to 0 vertex, which will be like a trivial random walk. So this is actually like the more general version. It's called like the abstract weighted simplicial complex. So I will give like a definition here about the weighted simplicial complex. So you can think of it like a collection of sets of some ground sets which are downwards closed, meaning that it's closed under taking subsets. Okay, so the dimension, if the dimension is n, then xn will be a collection of size n subset of certain ground step. And pi n will be some distribution we are interested in that we want to sample. Okay, so in the previous example, our n will just be 3 and xn will be all the 2 colorings of the graph. And for any smaller k, you can define xk to be the collection of all the size k subsets of the sets in xn. And also you can define a corresponding distribution, which is basically a distribution you obtain when you try to like draw a sample from a size n set and then just pick a uniformly random size k subset. So which is basically you generate, you have the pi n on the n sets, and then you do a downwalk and you to get a k set. This will define like the distribution of pi k. And so you can also think of it like a special case can be like a matroid, where all the xn will be the basis of the matroid, and all the xk are just size k independent sets of the matroid. Okay, and so this is like our example, but I'm only discussing it like for the 2 colorings, not the general simplicial complex. So our x3 are the 2 colorings of 3 vertices. x2 is like you choose 2 vertex and color them, and x1, x0. And our pi k distribution will be a distribution over a subset and the coloring of the set. And the distribution, the probability density will be obtained by 1 over n choose k, which is the probability of actually choosing this subset u, and times the probability sigma of u equals tau, which you think of it like the marginal probability that the subset u will receive the coloring tau. So this will be our simplicial complex in our setting. So how do we prove the convergence of the Glauber dynamics? Is by showing a certain like the entropy decay in this framework. Okay, so just recall that we use pi n to represent the target distribution, or say the distribution that we want to sample. And let's take any nu of n to be an arbitrary distribution of pi n. So you can think of this nu n as like the current distribution we have when we run the Glauber dynamics, or say like the initial distribution of the chain. And we will define a nu n-1, which is basically performing 1 step of the downwalk. So you choose an n set and removing 1 vertex, so you get n-1 set. And we will only need to show that when you do such a step, the entropy will contract with a rate of 1 minus beta. And so this will implies the modified log-Sobolev inequality and mixing time of the Glauber dynamics. So the reason is that this will kind of showing the KL divergence, were the case in So basically you perform a down work will be like half of a step of the Glauber dynamics. So this inequality here is showing that in half step of the Glauber dynamics, the entropy will decrease, the KL divergence from the current distribution to the target distribution will decrease. But then when you do the up work by the data processing inequality, the KL divergence will not increase. So this will show that in every step, the KL divergence will decay. And if we can show that with appropriate beta, with beta order 1/n, this will give like optimal constant for modified log-Sobolev inequality, which I won't define here, and also the mixing time of the Glauber dynamics. So that will be our like the main objective. Okay, and to show this type of condition, we will use this local to global approach, which have been like very well studied in the framework of high dimensional expanders. So the idea is that so you want to see how much the entropy KL divergence contracts between dimension n for n sets and dimension n-1 for n-1 sets. So a way to do it is actually like to consider this type of inequality for all k. So we know we already, so I think I defined like pi k, which is obtained by pi of n, and choose a random k set, k subset by performing the down work. You can also define the null of k in the same way, except that you start from the null n from the current distribution, take n set and take a k subset. Okay, so you can actually take this target inequality and consider it for any k. And for every such k, you can define this entropy contraction, which happens on dimension k between dimension k and k-1. And the contraction rate is beta of k. And our goal can be like, we can prove a bound on beta n by using, by recursively bounding beta n using beta n-1 and beta n-2 until like beta 1, which will be a trivial bound. So we only need to establish this type of recursive way of bounding the betas. And so if you do this type of thing, you can see that what you lose between beta k-1 and beta k is some factor of alpha k-1, which will be called the local entropy contraction rate. So this local entropy contraction rate can be think of as like you look at the link of the simplicial complex by considering like all the configurations with a fixed, say the red, the circle vertex is always red. You can consider like a simplicial complex with always containing the red circle, and this will gives like a subcomplex locally at some configuration. This is called the link, and you can define random walk on the link, which will be the local walk, and look at how much the entropy contracts in this local regime. And this will gives this alpha here. And then the spectral independence will be just be deduced from this local entropy contraction rate using some comparison between the variance and the entropy. And so this type of bound, actually they're like for variance or say for the eigenvalues, there have been a lot of previous work studying, trying to prove the contraction rate using local to global approach for high dimensional expanders. Here I just only mention a few. And in particular, the another really obvious foreign paper, they proposed this spectral independence basically using this local, but they only did like the variance contraction rate, or say for the eigenvalues. And for the entropy, there's also a paper of Guo-Mosa, which studied this like entropy contraction, but in the framework of matroid. But here we did like a little bit more, like a more general case when you have like any like spectral independence bound. Okay, so this will be like a very high level ideas. So the remaining of the talk, so I think I'll just be discussing very briefly about like how do we prove spectral independence for the hardcore model. So I've already discussed like when we know spectral independence, how does that implies the mixing? But there's another issue is like when, say, for the hardcore model, how do we prove that spectral independence holds? So I just use hardcore model as an example. So just recall that we have this influence matrix, which is like how much U changes the marginal probability of V, and spectral independence is bounding the maximum eigenvalue. Also, we want to do it for any inducible graph, which will correspond to an arbitrary conditional Gibbs distribution. And actually, most of the time when we prove like an eigenvalue bound for the influence matrix, what we actually do is bounding the infinity norm, which are like the absolute row sum. You look at the sum of the influence from a vertex to all the other vertices, and just try to give an upper bound on this quantity. This will also upper bounds the maximum eigenvalue. Okay. So for like the hardcore model, the way we prove spectral independence is by relating the original graph, the hardcore distribution of the original graph to the hardcore distribution of the self-avoiding walk tree. So this is like idea which was given by Weiss in the first proof, first algorithmic result for the hardcore model up to the uniqueness threshold. So we will consider this graph called the self-avoiding walk tree of a given graph. So you take a graph G and take a vertex R, and for you can generate like self-avoiding walk starting from the vertex R, which are all the walks that every vertex is only in the past for one, at most once. So no vertex will prior twice in a self-avoiding walk. So you can form all these passes and then form a tree called the self-avoiding walk tree, which is basically like branches when you have like different choice of the next step of the self-avoiding walk. Also, there will have like a certain boundary condition, so which will correspond to that when you try to actually move to another vertex that already appeared in the past, you will fix the configuration or the color of the vertices in a certain way. There's a certain rule to determine it. So our key result will be saying that on both the graph and the trees, if you look at the influence in the graph from a vertex, from the root R to another vertex X, this will be equal to the sum of influences from the vertex R to all the copies of vertices in the self-avoiding walk tree. So just to mention that, so in the self-avoiding walk tree, you consider all the paths. So every vertex will appear multiple times. They are called like copies of a graph, a copy of the original vertices, and the self-avoiding walk tree will be usually like exponentially large. So this will be a helpful lemma when you have many copies. So in particular, so Weiss shows that in both the tree and the corresponding self-avoiding walk, the marginal probability of the root are exactly the same. And our result can be like, think of it as like a generalization, which says that the influence from a vertex R to another vertex will be equal to the sum of influences. And so in particular, to show like the bound of influence from R to all the other vertices, you only need to do it now in the self-avoiding walk tree. So this reduces the problem from graphs to trees. And we can use a lot of previous results like the correlation decay approach or a strong spatial mixing proofs and adapt them to show spectral independence. Okay, just mentioned like, so this, what I just mentioned is like trying to use the correlation decay proof approach to establish spectral independence. There have been like also other type of research For example, you can use the path coupling for some local Markov chain and use that to show spectral independence. So the benefits is that usually if you have mixing time of some local MCMC, this does not immediately implies like an optimal mixing time bound of the Glauber, because usually you are just comparing spectral gap. And when you compare spectral gap, you always lose a factor of n. But with like a spectral independence, if you use spectral independence as a bridge, you can compare like the mixing time of some local MCMC with the Glauber dynamics. And also we can use the zero freeness of the partition function, which is the basis of the polynomial interpolation method. And we can use that to show spectral independence and also obtain some new result like the edge covers or even subgraph and other types of models. Okay, so this is like summary of how people can prove spectral independence. Now to conclude, or say more like an advertisement. So in the next two talks, you will hear like about more new techniques which try to improve the constant we have in this talk. So for our for the result we showed is that the Glauber for hardcore mixes in some constant times n log n, but the constant will depends on the maximum degree data. So this is not a polynomial bound when the maximum degree is like order n or n to the epsilon or even n to the epsilon. So there have been like a bunch of new results. And in the next two talks, there will be like entropy independence talk approach and also the localization scheme. And both of them combining with the field dynamics can be used to actually show that the Glauber dynamics for hardcore model will converge in n log n step with the constant does not depend on the maximum degree data. So it works for even for dense graph. So that way, like the more recent developments. So I think I just stop here. Thank you very much.